Good evening and welcome. I'm Madeline Rowe, and tonight we're going to take a long, relaxing journey through the science of Jupiter's Galilean moons. And if you enjoy these calm, evidence-based case files, subscribe, and there'll be another one waiting for you soon. There are worlds that introduce themselves with a single, clean identity. And then there are worlds that only make sense once you realise they were never meant to be understood one at a time. The Galilean moons belong to that second kind. At first glance, they are just 4 bright companions beside Jupiter, 4 steady points of light keeping the giant planet company in the dark. But the longer you stay with them, the stranger and more organised they become. One is a furnace pulled out of shape by gravity until rock turns restless and the surface can barely keep a scar. One is an ice shell written over with cracks and bands, where the most important landscape may be the sea no eye has directly seen. One is so large it outgrows every other moon in the solar system and keeps, improbably, its own magnetic field. And one looks old enough to remember nearly everything, a battered archive of impacts and silence that does not fit neatly into the same mechanical song as the other 3. They are not simply 4 moons around one planet. They are 4 outcomes of the same system, arranged by distance, heat, chemistry, and time. And tonight, we'll follow that arrangement gently, one quiet clue at a time. Back in my office, the stillness feels planetary, old and watchful, as though the room has been holding its place in the dark for a very long time. The lamp throws a circle of warm light over the desk, and at the centre sits a large folder marked The Galilean Moons. I draw it closer, lift the cover, and begin with the first notes. If you were to step outside on a clear night and look toward Jupiter through a small telescope, the first surprise would not necessarily be the planet itself. Jupiter is bright enough to command attention, of course, but the more delicate astonishment lies beside it. Tiny points of light lined up near the planet, changing position from night to night. That was the kind of observation that altered the shape of the universe in 1610. Galileo did not discover Jupiter, and he did not discover moons in the abstract. What he discovered was a fact that could not be made to fit the old tidy arrangement in which everything important circled Earth. Here were little worlds orbiting something else. However ordinary that sounds now, it was not ordinary then. It was destabilizing in the best scientific sense. A new observation had arrived, and the old map of the cosmos had to make room for it. There is something fitting about that beginning, because the Galilean moons still do that to us. They still refuse the first, simplest story. You might expect 4 moons formed beside one giant planet to resemble each other, the way siblings sometimes do when seen from a distance. Yet the real lesson of the Jovian system is that similar birthplaces do not guarantee similar lives. What matters is not only what a world is made of, but where it formed, how it moved, what kind of heat passed through it, how hard gravity kneaded its interior, what radiation swept over its surface, and whether its crust was allowed to stay still for long. Jupiter, in that sense, is not only a host, it is a shaping presence. To orbit Jupiter is to live within a hierarchy of forces. Its gravity, its magnetosphere, its tides, its plasma environment, and the repeated nudges of neighbouring moons. That is one reason the Galilean moons are often described as a kind of miniature planetary system. Not because they are tiny versions of Earth, Mars, or Venus, but because together they show divergence. Their differences are not cosmetic, they are structural. Io is largely rocky and dominated by ongoing volcanism. Europa is an ice world with a young surface and strong evidence for a deep ocean below. Ganymede is a mixed world of ice and rock, immense enough to carry a differentiated interior and an intrinsic magnetic field of its own. Callisto is also ice-rich, also large, but far more ancient in appearance, more weakly transformed, and less fully melted or reorganized inside. Each moon is a different answer to the question of what happens when matter settles into orbit around a giant planet and time begins its patient work. The easiest way to feel the logic of the system is to begin not with names, but with distance. The closer you orbit Jupiter, the stronger certain forces become. Gravity gradients become harsher. Tidal flexing becomes more intense. Radiation grows more punishing. The farther out you go, the gentler some of those influences become, though at the price of less tidal energy and often less internal drama. That gradient does not explain everything, but it explains enough to serve as the system's backbone. Near Jupiter, the world is hot, stressed, and constantly renewed. Farther out, surfaces hold onto old memories. In between, ice and rock negotiate with heat, pressure, and time in more complicated ways. Before we move one moon at a time, it helps to pause over the mechanical heart of the system, because without that heart, the diversity can look accidental. The key idea is resonance. Resonance is one of those words that sounds poetic until you see how exact it can be. In celestial mechanics, resonance means that orbital periods are related by simple ratios, and that those repeated relations allow gravitational effects to build rather than wash away. Io, Europa, and Ganymede are locked in just such a pattern. For every 4 orbits of Io, Europa makes about 2, and Ganymede makes about 1. This is often called the Laplace resonance, and it is not merely an elegant arithmetic curiosity, it is an engine. To understand why, imagine trying to settle into a perfectly circular orbit while 2 neighbouring worlds keep arriving at regular intervals to tug you slightly forward or back. If those tugs came at random, they would blur into noise. But in resonance, they do not come at random. They come on schedule. The schedule prevents the orbits from becoming perfectly circular. It preserves a little eccentricity, a little ovalness, a little departure from calm. And that little departure matters enormously. When a moon moves around Jupiter on an orbit that is not perfectly circular, the strength and direction of the tidal pull across its body vary slightly over time. The moon flexes. Its shape is kneaded rhythmically. Energy is dissipated inside as heat. This is the fundamental trick of the inner Galilean system. Orbital order creates internal disorder. The clockwork in the sky becomes warmth in the rock or ice. The most dramatic beneficiary of that process is Io, but Europa and Ganymede are tied into the same choreography. Even when most of the heating is strongest in the innermost moon, the resonance distributes consequences across the chain. One moon's tides affect the shared arrangement, and the shared arrangement affects all 3. In that sense, the inner Galilean moons are not separate stories placed side by side. They are coupled stories. Callisto, though, waits outside that coupling. It circles farther out and is not part of the present Laplace resonance. That fact may sound minor, but it is one of the most quietly important clues in the system. Callisto's distance leaves it with far less tidal heating than its siblings. Its surface, correspondingly, is not rewritten at anything like the same rate. Its interior seems to tell a different thermal story as well, one that may involve only partial differentiation rather than the more thorough internal sorting seen in the inner trio. If the Galilean moons are a family portrait, Callisto is the figure at the edge who makes you wonder whether everyone truly had the same upbringing. It almost certainly formed within the same broad Jovian environment, but its later history did not mirror the others, and formation models still wrestle with that difference. If there is a useful image for the resonance itself, it is not a chain made of metal, but a chain made of timing. Io hurries, Europa follows, Ganymede answers more slowly, and the pattern repeats. The tugs are never identical, yet they are never forgotten either. Over long spans of time, such patterns matter. They can migrate orbits outward, they can preserve eccentricities, they can keep interiors warm long after simpler worlds would have cooled, and perhaps in the far future, they may even pull Callisto into new resonant arrangements as the system continues to evolve. It is one of the humbling pleasures of celestial mechanics that even a system as old as Jupiter's can still possess a future dynamic drama waiting billions of years ahead. But for now, if we want to understand the system as it exists, we should begin where the resonance speaks most loudly. We should begin with Io. Io is the innermost of the 4 large moons, and almost everything about it feels like an answer turned up too high. Where the other large Galilean satellites wear ice across much of their surfaces, Io is a rocky world. Where the others preserve impact scars to varying degrees, Io has almost none worth speaking of. Where a cratered surface usually announces age and stability, Io announces the opposite. Its surface is too active to keep old records for long. Lava flows, plume deposits, sulfur frost, shifting vent systems, and relentless resurfacing erase much of the impact history that would otherwise accumulate. It is the sort of place that has not learned how to be still. That restlessness is not accidental, and it is not a leftover glow from formation. It is powered by tidal heating. Jupiter's immense gravity pulls on Io. Europa and Ganymede, through the resonance, keep Io's orbit from relaxing into a perfect circle. The result is continual flexing, and the flexing is so intense that Io has become the most volcanically active body known in the solar system. It is one of the most elegant causal chains in planetary science. A relationship in orbital periods produces interior heat. An interior heat produces a landscape in open rebellion against stasis. If you could stand far above Io and watch a long, accelerated history of its surface, it would not look like the patient impact gardening of the moon or the slow tectonic rearrangements of Earth's crust. It would look like a world perpetually revising itself. Dark plains would brighten with sulfur dioxide frost. Bright terrains would be overrun by lava. Plumes would rise, arch outward, and settle. Caldera-like depressions called paterae would expand or change character as underlying magma moved. Thermal anomalies would wander from place to place. Volcanic centers would flare to life, then fade, then reignite elsewhere. Even the colors can seem unreal to terrestrial eyes. Yellow, white, red, black, orange, greenish tints in places, all controlled by sulfur, silicates, temperature, and the chemistry of eruption and condensation. One temptation with Io is to think of it as simply hellish, as though its lesson is merely that too much heat ruins everything. But Io is more interesting than that. It is not a random inferno. It is an exquisitely forced world. The heat is generated in predictable relation to orbital mechanics. Its volcanism is not a failure of planetary order, but a consequence of it. That paradox is worth lingering over because it gives Io its scientific elegance. The most violent moon in the system is violent because the system is organised. Io also teaches another useful planetary lesson. Surfaces do not merely display interiors, they can conceal history by overprinting it. On many worlds, craters serve as clocks. The more craters, generally speaking, the older and less renewed the surface. Io breaks that habit almost completely. Its extreme lack of preserved impact craters tells us less about an absence of bombardment than about the efficiency of resurfacing. It has been struck, of course. The solar system does not spare it, but the evidence does not linger. Craters are buried, softened, or erased. The surface acts like a manuscript written over again and again until only the newest lines remain legible. Its mountains are a lovely complication too. When people hear most volcanic body, they often imagine a place made mainly of cones. But some of Io's large mountains are thought to arise from tectonic compression and faulting rather than from being ordinary volcanic edifices. In other words, the world is not simply leaking heat. It is also mechanically responding to the stresses that heat and gravity impose. The lithosphere can be lifted, broken, and tilted. The landscape becomes a conversation between eruption and deformation. Then there is the atmosphere, if atmosphere is the word one wishes to use for something so thin and so changeable. Io wears a tenuous envelope dominated by sulfur dioxide, fed in part by volcanic activity and in part by the sublimation of frost under sunlight. It is not the kind of atmosphere a person could ever confuse with Earth's, not even remotely, but it matters because it connects surface, plasma environment, and Jupiter's magnetosphere. Material from Io does not remain politely confined to Io. Sulfur and other products are fed into the surrounding Jovian environment, forming part of the plasma torus that threads around Jupiter. In that sense, Io exports its influence. It is not only shaped by the system, it helps shape conditions for the other moons as well. That outward influence matters especially when we move to the icy satellites. The surfaces of Europa, Ganymede and Callisto are not determined only by what rises from below. They are also altered by radiation, charged particles, and material delivered from outside, including sulfur-bearing compounds associated with Io's broader environmental effects. The Jovian system is not a set of sealed rooms. It is more like a building with shared air, shared vibration, and shared dust, each chamber retaining its personality but never existing in total isolation. Before leaving Io entirely, it is worth pausing over the space around the moons, because around Jupiter, emptiness is never truly empty. Jupiter does not merely sit at the centre of the system as a heavy anchor of gravity. It also surrounds itself with an enormous magnetic environment, a magnetosphere so vast that under the right conditions, it would stretch millions of kilometres into space. To live near Jupiter is therefore not only to orbit a planet, it is to move through an invisible weather system made of magnetic fields, charged particles, plasma, and radiation. The moons do not drift through silence. They drift through a medium that presses on them continuously. One of the reasons Io matters so much is that it helps feed that environment. Volcanic gases and particles escape from the moon and are then stripped, ionized, and caught up in Jupiter's magnetic domain. Sulfur and oxygen from Io become part of a torus of plasma encircling the planet, a ring of energetic material that does not stay politely separate from the other moons. Jupiter's fast rotation helps whip this plasma around, and the result is a system in which matter and energy are not confined to their places of origin. What erupts on one moon can become part of the operating conditions for another. This matters especially for Europa, Ganymede, and Callisto because their surfaces are largely icy, and ice is not a passive archive when bombarded by radiation. Charged particles strike the surface, break molecules apart, rearrange chemistry, sputter atoms away, and gradually alter what the uppermost layer is made of and how it looks. A surface exposed to Jupiter's magnetospheric assault is not simply sitting there preserving its own native composition. It is being processed. Sulfur compounds can be implanted. Water molecules can be broken into hydrogen and oxygen-bearing products. Thin exospheres can be maintained not by weather in the terrestrial sense, but by continual particle interactions at the surface. In the Jovian system, radiation is a geologic and chemical agent. That means that whenever we speak about the visible chemistry of Europa or Ganymede, caution is needed. A spectroscopic signature at the surface may tell us something about the ocean below, or about material emplaced from within. But it may also tell us about what Jupiter's environment has done afterward. The uppermost skin of an icy moon is a place of negotiation between inside and outside. Something may rise from below in a crack, a plume, or a warm pocket, and then be altered by sulfur implantation, irradiation, and sputtering until the original message becomes mixed with the edits of the surrounding system. The moon writes the first draft. Jupiter's magnetosphere makes revisions. Even the faces of the moons can diverge because of that constant environmental exposure. Leading hemispheres and trailing hemispheres do not always endure the same bombardment. A moon moving through plasma does not present every side equally to the incoming flow. Over very long spans, that asymmetry can help produce visible differences from one hemisphere to another. Changes in color, chemistry, brightness, and texture that are not purely about geology from below, but about encountered geometry from without. This is another reminder that a moon is not fully understandable as a solitary object. Its orbit decides what kind of weather it receives. Ganymede complicates that picture beautifully because it has an intrinsic magnetic field of its own. It does not simply sit exposed in the same way as Europa. Its local magnetic environment interacts with Jupiter's larger one, producing a nested structure, a moon-scale magnetosphere inside a planet-scale magnetosphere. It is a strange arrangement, almost architectural in feel, as if one room inside a building carried its own weather and pressure system. Auroral patterns near Ganymede's poles help reveal that deeper magnetic story, giving scientists another way to infer what the moon is doing inside and around itself. Callisto, farther out, receives a gentler version of this invisible weather. That relative calm is one reason its surface preserves old impact records so much better than Io or Europa. It is not only less tidally stressed, it is also less heavily processed by the harshest radiation environment closer to Jupiter. So when we compare the moons, we are comparing not just 4 interiors or 4 surfaces, but 4 positions within a magnetic empire. The conditions of nearness and distance matter twice over, once for tides and once again for radiation. Seen that way, Jupiter begins to feel less like a backdrop and more like a climate system for worlds. Not a climate of wind and rain, but a climate of fields and particles, of flexing and bombardment, of heat raised from within and chemistry revised from without. The Galilean moons circle through that climate in different ways, at different intensities, and their surfaces bear the consequences. By the time we arrive at Europa, then, we are no longer looking only at an ice shell. We are looking at an ice shell that lives under stress from below and under radiation from above. a surface written on from both directions at once. For all its scientific richness, though, Io is probably the least hospitable of the Galilean worlds in the conventional astrobiological sense. It is too dry now, too hot in the wrong ways, too stripped of the stable liquid water conditions that make habitability discussions meaningful. If Europa invites cautious hope, Io invites respect without comfort. It is a reminder that energy alone is not enough. A habitable environment needs the right kind of energy, the right kind of chemistry, and long-lived places where reactions can persist. Io has power in abundance, but not the sort that easily translates into a stable, water-rich biosphere. And so, after the furnace, the eye welcomes Europa almost as a relief. Europa is smaller than Earth's moon, but it carries one of the biggest reputations in planetary science. That reputation is not based on spectacle in the same way Io's is. Europa does not advertise itself through giant volcanic plumes visible at a glance or through riotous colour. Its power is subtler. It comes from the way the surface looks controlled yet interrupted, young yet broken, simple from afar and intricate up close. Europa's face is a shell of water ice cut by dark lineae, ridges, bands, disrupted blocks, and regions of apparent chaos where the ordinary order of the crust seems to have given way. To look at Europa is to look at a world where the surface behaves less like a quiet crust and more like a membrane under strain. Long cracks cross huge distances. Some appear to have opened and been filled. Some are paired ridges, as though material was pushed up along a split. Some bands seem to mark places where the icy shell separated and new material emerged or spread between the parted flanks. Chaos terrain takes that logic further. In such regions, the surface appears broken into rafts or plates of older ice embedded in hummocky younger material, as though portions of the shell were disrupted, rotated, and refrozen into new arrangements. There are debates over the exact mechanisms, and there should be, because Europa rewards careful disagreement. But the broad message is hard to miss. The shell has not been inert. The most important reason that matters is what it implies below. Europa is widely understood to possess a subsurface ocean beneath its ice shell. The evidence does not rest on a single dramatic proof, but on a convergence of clues. Magnetic measurements consistent with an induced field generated by a conductive layer, the moon's bulk properties, the geologic youth and deformation of the surface, and thermal models showing that tidal heating can help maintain liquid water beneath the ice. Taken together, these clues build a strong case that Europa is not merely icy on the outside. It is oceanic underneath. There is a special emotional force to the idea of an ocean under ice. It feels like a secret held in reserve. But scientifically, the important question is not simply whether liquid water exists. Liquid water by itself is a beginning, not a conclusion. The more interesting question is what kind of ocean it is. Is it in communication, directly or indirectly, with a rocky seafloor? Are there chemical gradients that could provide usable energy? Can oxidants produced at the irradiated surface find their way downward? Can materials from below find their way upward? Habitability, in the disciplined sense, is less about water alone than about water, plus chemistry, plus energy, plus persistence. Europa remains such a compelling target because it may satisfy more of those requirements than almost any other place beyond Earth. Its ocean is thought to be in contact with a rocky mantle, or at least to have a stronger potential for water-rock interactions than the deeper, more isolated oceans hypothesized for Ganymede and Callisto. That matters because when water meets rock in an active environment, chemical disequilibria can arise, minerals can alter, Gases can be produced. Redox gradients can develop. The quiet language of geochemistry begins to speak. On Earth, environments where water and rock interact under energy-rich conditions have long been treated as plausible settings for life's metabolism and perhaps for life's beginnings. Europa does not promise biology, but it keeps the door scientifically open in a way few worlds do. The surface helps sustain that interest because it appears young in crater terms. Europa does not carry the dense impact record of ancient, unrenewed terrain. Its sparse, larger craters suggest ongoing, or at least comparatively recent, resurfacing. There are places where the crust looks as though it has been stretched, spread, and reorganized. There are places where material from below may have approached or reached shallow levels. There are places where the distinction between tectonics and cryovolcanism becomes blurred in exactly the way one expects when working with ice instead of ordinary rock. Ice, after all, is not simply frozen water in the household sense. On planetary timescales and under planetary stresses, it can behave elastically, brittly, ductilely, convectively. It can crack, flow, weld, dome, and relax. Europa's skin records that complicated material behaviour across vast distances. There is also a tension built into Europa that makes it especially haunting. It lies within a harsh radiation environment. Jupiter's magnetosphere lashes it with charged particles. The surface is chemically processed, altered, darkened in places, irradiated. This is not gentle weathering. Yet that same hostile setting may help generate oxidants and other reactive products on the surface that could become chemically interesting if transported downward. Europa is, in that sense, a moon whose danger and promise are entangled. The same environment that makes its surface punishing also helps create ingredients that, in the right context, could matter for habitability. One must be careful, though, with the language of life. Europa is not evidence of life. It is not a proven ecosystem waiting under ice for a polite knock at the door. Even the word habitability should be handled with discipline. A habitable environment is not the same as an inhabited one. To say that Europa may have liquid water, energy sources, and potentially useful chemistry is to say that it meets some conditions we regard as important based on terrestrial biology. It is not to say that biology followed. The origin of life remains a harder and more stringent problem than basic habitability. On that point, restraint is not dullness, it is honesty. Still, Europa earns its reputation. It is one of those rare places where geology and astrobiology overlap so neatly that neither field can quite talk about the moon without borrowing some language from the other. A crack in the ice is not only a tectonic feature, it may be a clue about exchange between surface and subsurface. Surface salts are not only compositional curiosities, they may encode information about chemistry within or below the shell. Crater scarcity is not only a matter of age dating, it bears on the persistence of active processes. Europa makes almost every visible feature part of a larger hidden argument. And then, after Europa, comes the largest moon of all. Ganymede is a marvellous corrective to the assumption that moons must be small, supporting characters. It is larger than Mercury. If it orbited the Sun directly, stripped of its current station as Jupiter's satellite, it would still command serious attention as a planetary body. Yet what makes Ganymede especially rich is that it does not simply scale upward the properties of Europa or Callisto. It occupies its own middle ground. Partly ancient, partly renewed, icy and rocky, geologically altered, yet not in the same pattern as Europa. Magnetically unique, ocean-bearing in likelihood, but more internally layered and possibly more chemically isolated than the moon it is often compared to. The first thing many people learn about Ganymede is that it is the largest moon in the solar system, and the second is that it has its own magnetic field. That second fact is astonishing enough that it deserves to be felt properly. Ganymede moves inside Jupiter's vast magnetosphere, yet it maintains an intrinsic field generated by motions in a liquid metallic core. It effectively carves out a mini magnetosphere within a magnetosphere, a nested magnetic arrangement that sounds almost fictional until you remember that physics is happy to build such layered structures if conditions allow. Auroral observations and magnetic measurements help reveal this interior dynamo, making Ganymede unique among known moons. But if magnetism gives Ganymede a hidden grandeur, the surface gives it a visible one. Unlike Europa's comparatively uniform ice shell at first glance, or Callisto's overwhelmingly cratered old face, Ganymede presents a striking dark and bright terrain dichotomy. Some regions are darker, older, and more heavily cratered. Other regions are brighter and marked by grooved and tectonically modified terrain. The visual contrast alone makes you suspect a complex history, and the geology supports that suspicion. The dark terrains preserve records from early epochs, while the bright terrains tell of later deformation, resurfacing, and crustal renewal. Those bright terrains are especially important. They include broad-grooved bands made up of faulted, tectonically modified blocks, as well as smoother, bright units that some researchers associate with cryovolcanic emplacement or other resurfacing processes. If Europa's surface often feels like an active shell under ongoing strain, Ganymede's feels more like a world that underwent major episodes of reworking and left behind a patchwork memory of them. The exact balance between tectonic disruption, cryovolcanic resurfacing, and related processes is still being sorted out, and that uncertainty is part of the story. Ganymede is not geologically simple enough to reduce to one mechanism. It appears to have been shaped by several. There is a calm beauty in that mixed history. Imagine a moon where some regions preserve the battered old skin of early bombardment, while others have been split, tilted, buried, smoothed, or made bright through later activity. It is like looking at a city where one district preserves ancient stone, another shows reconstruction after fire, another bears the marks of carefully laid avenues, and the boundaries between them tell you when one era gave way to the next. Ganymede is that sort of planetary place. It does not offer a single clean face, because its history was not singular. Its craters themselves add further nuance. On icy worlds, impact features do not always behave as they do on rocky planets. Relief can relax, floors can arch, pits and domes can appear. Ancient structures can soften and flatten in ways that reveal how warm or weak the icy lithosphere once was. Ganymede and Callisto in particular display crater morphologies that remind us impact geology is never just about impacts. It is also about the material struck, the temperature of the crust, the viscosity of ice, and the timescale over which the surface can slowly deform after the moment of violence. A crater is an event, yes, but it is also a long afterlife. Beneath the surface, Ganymede likely contains a deep saline ocean. Yet habitability there is more complicated than on Europa. The likely presence of high-pressure ice layers between the ocean and the rocky mantle may reduce direct water-rock interaction. That matters because such interaction is one of the clearest routes to sustaining rich geochemical cycling. If the ocean is sandwiched between ice above and ice below, the chemistry may be less directly fed from the rock. There are hypotheses by which nutrients or volatiles might still be transported, and one should not dismiss those possibilities. But compared with Europa's more appealing possibility of an ocean in contact with rock, Ganymede can seem more layered, more insulated, more geochemically remote. At the same time, Ganymede's intrinsic magnetic field changes the comparison. It offers a degree of shielding from charged particles that Europa lacks at the same level. That does not make Ganymede easy or safe in any simple sense, but it complicates any ranking of astrobiological potential. Europa may offer better water-rock contact. Ganymede may offer different radiation conditions and a larger ocean volume. The point is not to choose a winner too quickly. The point is to see that icy worlds can be promising in different ways and limited in different ways. There is another reason Ganymede matters so much to the overall Galilean story. In formation models, it is often central to the question of migration and resonance capture. Its large size implies a dynamical importance. In some scenarios, Ganymede's migration relative to the others plays a leading role in establishing the present resonant chain among the inner three moons. In others, its contrasting interior history relative to Callisto becomes part of the puzzle of why two outwardly somewhat similar large icy moons did not end up thermally and structurally identical. Why is Ganymede more fully differentiated? Why does Callisto appear only partially so? Why are their surfaces so different? Size alone is not enough to answer. Timing, accretion history, heating, and migration all enter the argument. If Io is the system's fire and Europa its hidden sea, Ganymede may be its archive of transitions. It preserves evidence of ancient terrain, major tectonic episodes, possible cryovolcanic resurfacing, deep interior evolution, and magnetic activity all at once. It is a moon that asks not for a single headline, but for a layered reading. And that layered reading brings us naturally to the last of the four, the one whose quietness is deceptive. Callisto has often been described as the most ancient-looking of the Galilean moons, and that judgment is not merely a matter of mood. Its surface is heavily cratered and comparatively little modified by endogenic resurfacing. Where Io seems unable to keep a scar, Callisto keeps scars almost compulsively. Where Europa advertises fracture and exchange, Callisto offers age. Where Ganymede splits itself between bright alteration and dark inheritance, Callisto leans heavily toward inheritance. It is a world whose first impression is durability. That durability, however, should not be mistaken for perfect simplicity. Callisto is not just an inert ball of dirty ice. It is better thought of as a world where impact processes, sublimation-driven modification, long thermal history, and limited internal activity combined to preserve a different sort of planetary record. Its surface includes gigantic impact structures, the most famous being Valhalla, a multi-ring basin of extraordinary scale. Features like that do not simply testify to being hit. They also reveal how ice-rich lithospheres respond to impact differently from rocky crusts. Relief is lower than one might expect from analogous rocky basins. Craters can be shallow, relaxed, or morphologically unusual. Old structures can be softened by the rheology of ice over time. If Io is the world that keeps no diary, Callisto is the world that keeps too many pages. Every impact basin, every cratered plane, every subdued ring structure asks to be read as part of deep time. But Callisto's silence is not total. There are hints, still debated, that some limited tectonic features may exist in places. There are questions about whether certain fissures or lineaments are purely impact-related or might reflect modest internal stresses. The present data are incomplete enough that caution is wise. Compared with Europa and Ganymede, Callisto remains underdescribed at high geologic detail. Its quietness is real, but some of its subtlety may still lie below the resolution of our older images. The interior tells the more provocative story. Callisto appears to be only partially differentiated, which means its materials may not have fully separated into neat internal layers the way they did in Io, Europa, and Ganymede. That alone makes it scientifically precious, because partial differentiation hints at a different accretion or heating history. Perhaps it formed more slowly. Perhaps its accretion energy was distributed in a way that avoided complete interior melting. Perhaps the timing of radionuclide heating differed enough to preserve a mixed interior. However the exact story is told, the message is the same. Callisto seems to have escaped some of the thermal reworking that transformed the others. And yet, paradoxically, it may still possess or have possessed a subsurface ocean. Magnetic evidence has long suggested the presence of a conductive layer consistent with salty liquid water at depth. If so, Callisto becomes a moon with an old, battered exterior and a hidden fluid interior, an unlikely pairing to eyes trained by simpler worlds. But again, the details matter. Any such ocean may sit above high-pressure ice layers that separate it from the rocky mantle. That separation limits direct chemical exchange. Radiogenic heating, rather than strong tidal heating, would have to do much of the work of maintaining liquid water, perhaps aided by salts or ammonia lowering freezing temperatures. Some models allow a persistent ocean. Others allow that it may have partially or wholly refrozen over long spans. Callisto is therefore not absent from habitability conversations, but it enters them more quietly and with more caveats than Europa. Its environment is quieter too. Because Callisto orbits farther from Jupiter, it spends much of its time outside the most intense regions of Jupiter's main plasma sheet. The radiation environment is gentler than at Europa or Io. That fact has practical implications for future exploration concepts, which is one reason Callisto sometimes appears in discussions of possible staging areas or less punishing operational environments in the Jovian system. But scientifically, it also reinforces its outsider status. Callisto is less heat-stressed, less radiation-battered, less tidally forced. The very things that make it calmer also make it different. And because so much of the most important Jovian science is hidden, the method matters almost as much as the conclusion. None of us has watched Europa's ocean directly. No one has stood on Ganymede with a drill. No one has cut through Callisto's crust to inspect its internal layers. The Galilean moons teach a quiet scientific discipline: how to infer deep structure from surface clues, magnetic behavior, gravity, density, and motion. They are good worlds for remembering that astronomy and planetary science are often arts of indirect seeing. The first layer of that indirect seeing is simple bulk measurement. If you know a moon's size and mass, you can calculate its average density, and from density you begin to narrow the possibilities. A body made mostly of rock cannot masquerade as one made mostly of ice, at least not in the broad sense. That is one reason the Galilean moons already begin to separate from one another before we ever map a crack or count a crater. Io's high density points toward its rocky nature. Europa, Ganymede, and Callisto, with lower average densities, announce larger fractions of water ice and volatile material. At the coarsest scale, even that is enough to tell you you are not looking at 4 copies of the same world. But density only begins the conversation. The next question is whether the interior stayed mixed or sorted itself out. Differentiation is the term for that sorting. Denser materials sinking inward, lighter materials rising outward, the body developing more distinct layers through internal heating and partial or extensive melting. Ganymede appears to have differentiated substantially, enough to support a metallic core and a dynamo. Io, too, is strongly differentiated, Europa is understood to be differentiated as well. Callisto, by contrast, seems to have remained only partly so, with less complete internal separation. That difference matters because it encodes thermal history. A thoroughly differentiated moon is usually telling you that enough heat once moved through it to reorganize its deep interior. A partially differentiated one is telling you the opposite, or at least telling you that the heating history was more limited, slower, or differently distributed. Gravity helps refine that picture. A spacecraft flying past a moon does not move through empty mathematics. It responds to the moon's gravitational pull in a way that reveals how mass is distributed inside. Slight changes in trajectory, carefully tracked by radio, allow scientists to infer whether a body is more centrally concentrated or more uniformly mixed. It is a patient kind of measurement, almost clerical in appearance, but it opens a door into the unseen. The spacecraft does not need to touch the deep interior. It only needs to pass near enough, precisely enough, and be listened to carefully enough. Magnetic measurements add another layer, and for Europa, Ganymede, and Callisto, they have been especially important. In a changing magnetic environment like Jupiter's, a conductive layer inside a moon can generate an induced magnetic response. This is a subtle and beautiful idea. The moon does not need to produce its own permanent magnetic field to reveal a hidden ocean. It only needs to contain a conductive layer, such as salty liquid water, that reacts to the shifting external field around it. When the measured magnetic behavior matches what such induction would predict, a concealed ocean becomes one of the strongest explanations. That is a large part of why Europa's ocean is taken so seriously, and why subsurface liquid layers have also been discussed for Ganymede and Callisto. On Ganymede, of course, the story becomes more intricate because there is both induction and an intrinsic field generated by the moon itself. That makes the measurements harder to interpret at first glance, but more rewarding in the end. The moon is not simply passively responding to Jupiter's field, it is contributing its own internal signature. Untangling those signals requires care, but care is exactly what these worlds demand. Surface geology then serves as a kind of corroborating witness. A young, fractured crust, low crater densities, evidence of extension or resurfacing, and terrains that suggest movement within the ice shell all strengthen the case that a moon is not frozen solid from surface to centre. Europa's lineae, bands, and chaos terrains are not proofs of an ocean in isolation, but they are profoundly consistent with one. Ganymede's tectonically modified bright terrains tell of an interior that was once more active than a cratered old surface alone would suggest. Callisto's subdued ancient face, by contrast, speaks of limited resurfacing, which is why the notion of a hidden ocean there feels more surprising and more dependent on geophysical inference than on obvious exterior youth. Even impact craters become instruments in this kind of reasoning. On icy worlds, crater shapes are controlled not only by the violence of impact, but by the properties of the crust and the warmth below it. A warm or weak icy lithosphere can relax topography over time. Basin rings can soften, slopes can slump. Central structures can look unlike their rocky equivalents. In this way, a crater is not just a scar from above, it is a probe of the material beneath. The surface remembers the impact, but it also reveals how the crust responded afterward. That response is part of the moon's internal biography. Then there is spectroscopy, which sounds austere until one remembers what it means in practice, reading light for chemistry. Reflected sunlight and emitted radiation can reveal water ice, salts, sulfur-bearing compounds, organics in some contexts, grain size differences, and thermal anomalies. On Io, thermal emission helps identify volcanic hotspots and active regions. On Europa and Ganymede, spectral data help distinguish cleaner ice from more contaminated terrains and raise questions about what materials may have come from below versus what materials were implanted or altered from above. Light, carefully separated into wavelengths, becomes a way of feeling composition at a distance. All of this is why the Galilean moons have always been such excellent scientific worlds. They are not only interesting in themselves, they are legible through multiple independent methods. Gravity says one thing, magnetism says another, geology adds a third, spectroscopy a fourth, and orbital dynamics a fifth. The strongest conclusions are the ones where those lines of evidence converge. A moon begins as a point of light in a telescope, then becomes a body with a measured mass, then a mapped surface, then a magnetic problem, then a thermal history, then a candidate ocean world, then a chapter in the larger question of how planetary systems work. The knowledge accumulates layer by layer, very much the way the worlds themselves accumulated. So before we return to the broader architecture of the system, it is worth appreciating that these moons are not only objects of wonder, they are objects of method. They have taught scientists how to build confidence in hidden things without pretending that hidden things are already fully known. That is a quieter achievement than discovering a volcano or announcing an ocean, but in some ways it is the deeper one. It is the reason these worlds can keep their mystery without becoming vague. We do not know everything about them, but neither are we guessing in the dark. There is something almost literary in the arrangement of the four moons when seen in order. Closest in, a dry, volcanic world. Next, an icy world with a likely ocean and a fractured shell. Then a giant mixed world with a magnetic heart and a complex resurfacing history. Finally, an old cratered archive with the possible memory of hidden water, but fewer obvious signs of renewal. It is difficult not to read that sequence as a gradient, though it is never a simple one. Distance from Jupiter matters. Composition matters. Resonance matters. Formation timing matters. The beauty of the Galilean system is that all of those variables are visible at once if you are patient enough. At this point, it is worth stepping back from individual moons and seeing how they talk to one another as a set. One of the strongest cross-cutting themes is resurfacing. Io resurfaces so aggressively that impact craters are almost absent. Europa resurfaces enough to keep its crater density low and its surface geologically young in appearance. Ganymede shows ancient terrain, but also major tectonic and perhaps cryovolcanic overprinting. Callisto preserves the old cratered state most faithfully. In a single planetary neighbourhood, then, we can trace a spectrum from nearly total erasure of ancient surface record to profound preservation of it. That is enormously useful for comparative planetology because it lets us ask the same basic questions under very different thermal and material conditions. Another theme is the relation between surface and subsurface. On all four moons, the exterior can mislead unless read carefully. Io's surface says heat, but not habitability. Europa's surface says ice, but also oceanic possibility. Ganymede's surface says mixed history, which points toward a layered interior and a magnetic engine. Callisto's surface says dormancy, yet the interior may still harbour liquid. The visible face is never the whole story. This is one reason planetary geology is so often a detective discipline. One is almost always working from partial exposure, inferring hidden structure from cracks, crater forms, compositional signatures, gravity, magnetism, and thermal plausibility. A third theme is the role of exogenic and endogenic processes together. A moon is shaped from within by heat, differentiation, melting, tectonics, and volcanism or cryovolcanism. But it is also shaped from without by impacts, plasma, radiation, sputtering, and the delivery of foreign material. The Galilean moons make that dual authorship especially obvious. Europa's surface chemistry is not simply a direct sample of its ocean because radiation alters it. Callisto's dark lag deposits and sputtering environment complicates simple readings of composition. Io's sulfur-rich products influence the wider Jovian environment and can in turn affect other surfaces. Even Ganymede's oxygen exosphere and surface processing are tied to interactions with particles and magnetic fields. The moons are self-made and system-made at once. All of this leads naturally to the question that sits behind them. How did such a set of worlds form? The modern broad answer begins with a disk around Jupiter. As Jupiter was forming and accreting gas in the young solar system, a circumjovian disk of gas and solids likely surrounded the planet. Within that disk, seeds of moons could grow by accreting smaller solids, whether one prefers to emphasize satellitesimals, pebbles, or a mixture depending on the model. In that picture, the Galilean moons did not simply condense where they now sit and stay put forever. They likely formed in a more dynamic environment in which migration through the disk mattered, growth timescales mattered, and the structure of the disk itself shaped what materials were available at different distances. This is where the system becomes both more powerful and less fully settled. Formation models are not mere afterthoughts tacked onto the present arrangement. They are attempts to explain why the present arrangement looks the way it does. Why are the masses of the Galilean moons comparable in the rough sense that no single moon utterly dominates the others? Why do the inner three participate in the resonant chain while Callisto does not? Why are Io, Europa, and Ganymede fully differentiated while Callisto appears only partially so? Why do the ice fractions and densities vary with position the way they do? These are not separate questions. They are one formation problem viewed from multiple angles. One attractive family of ideas imagines the moons forming farther out in the circumjovian disk and migrating inward as they interacted gravitationally with the gas. In such scenarios, the inner three can be captured into resonance sequentially as migration brings them together. That helps explain why resonance among Io, Europa, and Ganymede feels so orderly. It may not be an accidental late arrangement, but a natural outcome of convergent migration and capture. A stopping mechanism near the disk's inner edge or cavity can then help prevent the moons from simply spiraling into Jupiter. Such models have a pleasing logic, though the exact nature of the stopping mechanism and the disk environment remains an active area of work. The temperature gradient in the circumjovian disk also matters greatly. The inner regions would have been warmer, making it easier for inner moons to lose more of their volatile inventories, while farther out, colder conditions would allow more ice-rich bodies to form or survive. That fits at least broadly with Io's rocky, largely anhydrous state, and the greater ice content of Europa, Ganymede, and Callisto. But broad fits are not the same as final answers. One must still explain the details, including how much water Europa retained relative to Io, why Ganymede and Callisto, though both ice-rich and fairly similar in size, diverged so strongly in internal evolution, and why Callisto remained outside the present resonance chain. Callisto is the moon that keeps any formation theory honest. It is easy, comparatively speaking, to tell a tidy story for the inner three: migration, capture, tidal heating, differentiated interiors, and so on. But Callisto stands nearby asking inconveniently specific questions. If inward migration and resonance capture were so natural, why is it not resonant now? If Ganymede and Callisto formed from similar ingredients, why is one more fully differentiated and tectonically modified, while the other remains comparatively primitive? Some models suggest that Callisto formed later or more slowly, allowing short-lived radioactive heating to diminish before enough accretional heat could fully melt the interior. Others emphasize pebble accretion or surface-released energy in ways that preserve partial differentiation more readily than older satellitesimal scenarios. Still, others explore the details of migration, disk dispersal, and the timing of resonance capture. None of that means the origin story is confused beyond use. It means we are fortunate enough to be looking at a system rich enough to exclude overly easy explanations. The present best broad picture is that the Galilean moons formed within Jupiter's circumplanetary environment, migrated, interacted, and in the inner three achieved the resonant architecture we see today. But the details of Callisto's history, and the precise thermal divergence between Ganymede and Callisto, remain among the most interesting unresolved parts of the story. There is also a longer-term dynamical twist that gives the system a kind of afterlife. Tidal dissipation, especially in the Jupiter-Io pair, continues to redistribute energy and angular momentum through the resonant chain. Over immense timescales, this leads to orbital migration. Models of the system's future suggest that as Ganymede moves outward, it may eventually encounter resonance with Callisto, and in many simulations, some form of resonant capture occurs. That is a future billions of years away, not a near-term event, but it is deeply satisfying in a scientific way. The present arrangement is not static furniture. It is a moment in a long, dynamical history. The Galilean moons are still in slow motion, becoming. And that matters because it reminds us not to treat the current system as the only possible or inevitable configuration. The Laplace resonance among Io, Europa, and Ganymede has a history and a future. Callisto's present non-membership may itself be temporary on geological timescales. Even a stable-looking system can be evolutionary if one grants it enough time. Astronomy often teaches patience by force. Things that seem fixed at human speed become fluid at planetary speed. If one were trying to summarize the 4 moons in a single sentence each, it might go something like this. Io is what tidal heating can do to rock when resonance never lets the interior rest. Europa is what an ice shell looks like when a hidden ocean and ongoing stress keep interrupting the surface. Ganymede is what happens when a large icy moon differentiates deeply enough to sustain a core dynamo while preserving a patchwork of ancient and renewed crust. Callisto is what remains when an outer moon escapes most of the tidal violence and stores the memory of early bombardment far more faithfully than its siblings. But even those sentences are only beginnings, because each moon also works as an analogy for a broader category of worlds. Io teaches us about tidal volcanism and interior dissipation. Europa teaches us about ice shell tectonics, ocean worlds, and the cautious logic of habitability. Ganymede teaches us about magnetic dynamos in unexpected places and the geological middle ground between total reworking and near-total preservation. Callisto teaches us about partial differentiation, old icy crusts, and the quiet scientific value of worlds that do not seem eager to perform. Together, they broaden the vocabulary of planetary science beyond the rocky planets that dominated so much early intuition. It is remarkable, really, how much of modern planetary thinking has been forced to expand because of moons. For a long time, planets felt like the main stage, and moons like secondary players. But then the solar system kept producing moons that refused supporting roles. Titan with its atmosphere and methane cycle, Enceladus with its south polar plumes, Triton with its captured strangeness, and before many of those came fully into focus, the Galilean moons were already there, quietly insisting that moon does not mean simple. Jupiter's 4 large satellites helped teach us that complexity is not reserved for planets with famous names. If we return for a moment to the office metaphor from the beginning, we can improve it now. The desk at first looked like a planet in the middle and 4 folders around it. That was not wrong, just incomplete. The truth is that the folders are tied to one another with fine thread. Tug the I/O folder and Europa shifts slightly. Tug Europa and Ganymede answers. Leave Callisto outside the thread, and you still must account for why. Dust from one folder lands on another. Heat in one changes the logic of the set. The arrangement is not a still life after all. It is a system of correspondence, and perhaps that is why these moons are so soothing to think about, even when some of them are violent. They reward orderly attention. They are not random wonders scattered around Jupiter for decoration. Their diversity comes from identifiable causes: distance, resonance, composition, radiation, heat flow, and time combined to produce legible outcomes. The more closely you look, the more the differences stop feeling chaotic and start feeling earned. There is still much we do not know, and some of the most interesting uncertainties are observational rather than conceptual. Better topography, better spectroscopy, better gravity and magnetic constraints, and better imaging will refine many of the questions I have let remain soft around the edges tonight. On Europa, the details of surface-ocean exchange, the shell structure, and the interpretation of specific terrains will sharpen. On Ganymede, the balance between tectonics and cryovolcanism, the structure of the ocean layers, and the implications of its magnetic field will become clearer. On Callisto, high-quality observations may finally show whether its apparent geological minimalism is as complete as it now appears, or whether subtle records of internal evolution have been hiding in the low contrast all along. Even Io, so obviously active, still contains open problems about magma transport, resurfacing patterns, plume chemistry, and the exact balance of internal processes. That is one reason missions to the Jovian system remain so scientifically potent. They are not going there to admire 4 familiar worlds and confirm what everyone already knows. They are going because the Galilean moons sit right at the intersection of planetary geology, celestial mechanics, ocean world science, magnetic physics, and the search for habitable environments beyond Earth. Few destinations offer that many disciplines at once. Few systems let one compare 4 large related bodies under one giant planet's rule and watch so many principles of planetary science express themselves in parallel. And there is, quietly, a philosophical lesson in that as well. We often want nature to simplify itself for us. We like categories that hold still: rocky world, ice world, old world, active world, habitable world, dead world. The Galilean moons let you use all of those phrases, but never with complete comfort. Io is active, but not hospitable. Europa is icy, but perhaps oceanic and chemically alive in a prebiotic sense. Ganymede is magnetized and immense, but maybe more internally isolated than a first hopeful glance would suggest. Callisto is ancient and quiet, yet may still conceal liquid water. The categories work only if we allow them to overlap and remain conditional. That conditional quality is not a weakness in science, it is its grace. To say that Europa may be habitable is not indecision, it is accuracy. To say that Callisto may host a conductive ocean, but with more limited chemical exchange, is not hedging for the sake of hedging. It is respect for the structure of the evidence. The Galilean moons, perhaps more than many astronomical subjects, reward that respect. They are worlds best approached with enough imagination to care and enough discipline not to overstate. If I had to choose the most beautiful single idea in the whole system, I suspect it would still be the transformation of orbital timing into geology. The notion that repeated gravitational tugs can keep a moon warm, fracture ice, sustain an ocean, or drive volcanism seems almost too clean to be real. And yet, there it is. A ratio in the sky becomes a crack in the crust. A resonance becomes a lava plain. A slight eccentricity becomes an ocean that does not freeze. It is the kind of scientific connection that feels both abstract and intimate at once, as though mathematics reached down and left fingerprints on the landscape. And if I had to choose the most humbling idea, it would be this. Even here, in a system watched since the age of telescopes began, the full story is not finished. We know enough to be astonished properly, but not enough to stop asking. We know that Io is violently active, but not every detail of how its interior circulates. We know that Europa likely hides an ocean, but not the full architecture of its shell or the traffic between surface and sea. We know that Ganymede's heart generates a magnetic field, but not every chapter of how its outer crust was renewed. We know that Callisto is quieter and more primitive, but not exactly why its path diverged from Ganymede so decisively. The system remains generous with clues and economical with finality. That seems appropriate for Jupiter. A giant planet ought to keep some scale in reserve, some mysteries that do not flatten at first contact. Its 4 great moons have always been more than ornaments. They are laboratories arranged in order. They are a memory of the early solar system, a study in tides and ice and rock, and a set of arguments about how worlds can diverge under shared parentage. They are also, somehow, still what Galileo first saw. Small lights near a brighter one, changing place from night to night, asking the observer to notice that motion means relationship. Back in the office, the folders have not moved, but they no longer look still. The one nearest the lamp feels too warm, as though the pages inside never stop rewriting themselves. The pale, cracked one seems to hold water in its silence. The broad, heavy one has the strange dignity of a thing large enough to make its own weatherless shield. And the farthest one, old and quiet, turns out not to be empty of surprise at all. The desk is only wood, the folders only paper, but the pattern they imitate is enough for one evening. Outside the window, the sky remains what it has always been, dark enough to hide most of its details until someone is patient enough to ask for them. Jupiter hangs out there with its companions, not as decorations, but as evidence. Evidence that worlds can be linked by rhythm. Evidence that heat can come from motion instead of nearness to a star. Evidence that oceans can hide below ice, that magnetism can belong to a moon, that ancient surfaces can preserve one history while concealing another below. Evidence, too, that the solar system is less tidy and more interesting than any first map ever suggested. And that, for tonight, is enough. The lamp is low. The 4 folders rest where they are, each altered by the one in the middle, each different from the others, each part of a system that makes more sense the longer you look. So we can let Jupiter keep its moons for now, and let the moons keep their heat, their ice, their magnetism, their scars, and their silence. We have followed them as far as we need to for one quiet night, and now, at last, we can close the file. The